So welcome everyone to this new episode of the Protochip Flash Talk series. Today I would like to present you our recent work about the synthesis and characterization of high-entropy-alloy based macro and mesoporous materials. So let me start with a few words of introduction. Usually high-entropy alloy are defined as multimetallic alloys in which every metal is present in a concentration ranging between 5 and 35% atomic concentration, or with a mixing entropy which should be equal or higher than 1.5 times the molar gas constant. Thanks to their complex structure, this kind of materials present a very vast number of different surface sites with different composition, which in combination with the lattice distortion effect on the surface of the materials make them a very interesting platform for the discovering of new catalysts. Typical synthetic approach to high-entropy alloy require very high temperature, which is needed to achieve a state in which the entropic contribution to the mixing free energy is predominant, followed by rapid quenching to room temperature in order to stabilize the high temperature, high entropy phase in room condition. Of course, when we are looking at catalysis, we want to increase the specific surface area of our materials in order to maximize the catalytic activity. And therefore, a common approach is to produce aluminum-based alloys, which then undergo dealloying to obtain porous high-entropy alloy. In this work, we actually developed a new strategy, which is inspired to the sol-gel synthesis of porous, to the templated sol-gel synthesis of porous oxide, and in which basically we start from an aqueous solution containing dispersion of polymer particles, which we call our latex template, combined with our molecular precursor. In this work, we choose to work with the noble metals from the platinum group. So here you can see that we started from noble metal chlorides. This aqueous solution is then sprayed with a heated nozzle to produce an aerosol of droplets of different sizes. Upon water evaporation from the surface of the droplets, the polymer particles self-assemble to form superstructure, which are embedded in the matrix composed by our metal salt. Here you can see an SCM picture representing this kind of objects. If we take this object and then anneal them under inert atmosphere at a temperature of 500 degrees or lower, we obtain porous metallic particles, as you can see in this image. Of course, the advantage of this method is that we can easily tune the size of the pores by changing the size of our polymer template particles. For instance, in this case, we started with 30 nanometers polystyrene template particles, and with our 5 different platinum metal group salts. When we take this particle and anneal them at 500 degrees under argon, we obtain this porous structure that the nitrogen absorption and desorption analysis revealed to be mesoporous, with pores comprised between 50 and 2 nanometers then, and with a specific surface area of 150 square meters per gram. X-ray diffraction patterns reveal that these porous particles are actually composed by a single phase with a phase center cubic symmetry, which is typical of platinum group metals in their metallic state. And when we take a closer look to our porous structure, we can actually see that the particles are composed by porous particles are composed by tiny nanocrystals of about 5 nanometers in diameter with the phase center cubic structure. So scanning transmission electron microscopy characterization coupled with energy dispersive X-ray spectroscopy revealed that the 5 metals that we used are actually homogeneously distributed across the whole structure, and the mixing looks homogeneous even at the scale of 2 nanometers. We quantified the presence of each metal by combining energy dispersive X-ray spectroscopy analysis with the X-ray fluorescence. And in both cases, we obtained similar results with metal ranging between 25 and 30% in atomic concentration, which was exactly within the definition of high-entropy alloy. In order to understand if our structure, if our porous alloys are actually composed, if all the metals are actually mixed at the atomic scale within our porous high-entropy alloy, we also perform time-of-flight secondary ion mass spectroscopy. In this technique, primary ion beam of pentabismuth ions that you can see here is used to produce secondary ions from our multimetallic alloys. And then these different ions are analyzed with a time-of-flight analyzer according to their mass to charge ratio. We can see that we use a porous ruthenium reference as a reference materials, and we can see here clearly the peak corresponding to the distribution of the ruthenium 3+ species. However, in the case of our multimetallic alloys, we can see that also other clusters are present, which may be attributed to the bimetallic cluster ruthenium platinum here, or to the trimetallic cluster ruthenium to rhodium plus here. So to recapitulate on the synthetic part, we can see that with this method we achieve metal reduction, metal alloying, and the production of porosity in one step during thermal annealing. And especially the porosity, being able to produce porosity, it's really important for catalytic application of multimetallic alloys. And to show this importance, we choose to study one model reaction, which is the carbon monoxide oxidation to carbon dioxide reaction, which is a thermocatalytic reaction in which temperature activates the oxidation of CO2. And we can see in this graph that when we use our macroporous and mesoporous high-entropy alloy-based materials, the temperature at which the reaction starts, at which the conversion of CO to CO2 reach 50% is drastically decreased compared to the to non-porous particles, so to high-entropy alloy particles, reference particle without porosity, and compared to the non-catalyzed reaction. So, of course, however, when we have this kind of porous materials and we perform catalytic reaction on them, we wonder which is the evolution of the structure in terms of porosity and in terms of alloying as a function of the temperature, because these are temperature-activated catalytic reaction. And in order to understand the stability and the evolution as a function of the temperature, we carried out in situ transmission electron microscopy characterization of this material with the Protochip gas holder system. In this system, TM sample holder from Protochip is connected with a gas supply system from which we can choose different gas, inert as well as reactive gases, and the sample holder can be heated up to 1000 degrees and operated at a pressure of 1 bar. The sample holder is also composed of two different chips, which are in which there is a transparent window composed of silicon nitride on which we deposit our particles that we want to observe, and heating system composed of silicon carbide. And another chip with a silicon nitride window is closed on top in order to achieve a closed system. In this kind of closed chamber under the flow of gas, inert or reactive gas, we can observe with the electron beam the evolution of materials as a function of the temperature. These are the results of these studies that you can see in this slide. Basically, here you can observe one single pore from our porous particles. Here you can see the walls of the pore, and you can observe that between 300 and 300 degrees, there is a significant shrinkage in the volume of the pore, which is actually due to the reduction of metals from metal chloride, so metals with oxidation state 3 or 4, to pure metals. We know from XPS analysis that at 300 degrees the metals are not fully reduced, but at 350 degrees all the metal are fully reduced. So this volume shrinkage can be attributed to complete completion of metal reduction. And then we can see that up to 600 degrees, the structure is quite stable. We observe increase in crystallite size between 600 and 800 degrees, while at 900 degrees, the porous structure is totally lost. The same trend can be observed for a bigger fragment of particles with several pores in it. We still observe a shrinkage in the volume, but we observe a stability of the porous structure up to 900 degrees. Concerning the metal alloying, we can see that these five metals actually stayed homogeneously mixed within the whole structure during the whole span of the Gaussian range of temperature that we investigate. Even at 900 degrees, when the porous structure is completely lost, we can still see that the five metals are homogeneously alloyed. So this study gives us an insight into the stability of this porous material composed of five noble metals. And the natural continuation of this kind of study will be, of course, to study the stability of these multimetallic porous particles under a flow of reactive gas, which is also possible with the protochip system. And this will be also the perspective of my future research at the Institut de Physique et Chimie de Matériaux de Strasbourg. And with this, I would like to conclude my presentation here and would like to thank all of you for your attention, as well as my collaborator for this work that I just presented.